So, last video we have seen two examples of hyperbolic partial differential equations. We reduced them into canonical form, and one you could reduce but you could not solve it. Other example we have considered is a simpler one, that is wave equation, which is already in the canonical form, one canonical form. You can get the solution of that equation by reducing into another canonical form, another hyperbolic canonical form. By reducing that into another canonical form, we could solve the partial differential equation completely. Okay, we can find the general solution of that equation. We have given that example, those two examples, in which one you cannot find the general solution, other example you reduce into canonical form and find the general solution. Okay. So, in this video we will see other cases when the partial differential equation is elliptic and parabolic case, how do you reduce partial differential equations with variable coefficients, and each when this partial differential equation is elliptic or parabolic, how to reduce. We will work out how to get its canonical form in this video. Okay. So, we will consider this example, example number 3. So, see, we will start with the parabolic case. So, parabolic case is so reduce x square uxx plus 2xy uxy plus y square uyy equal to 0 into canonical form. So, again, so you consider so procedure we know. So, you start with A is x square, B is 2xy, C is y square. Discriminant is b square minus 4ac is 4x square y square minus 4ac is again 4x square y square, that is 0. So, for every xy in the plane, this partial differential equation defined is 0. Okay. Discriminant is 0. So, the equation is clearly parabolic. In the parabolic case, we have seen that new variables are coming only from, you could get one variable xi or eta. So, xi you can get from the partial from the ordinary differential equation, that is dy by dx equal to b is 2xy plus or minus 1 is plus square root of b square minus 4ac, that is 0, okay, divided by 2ax square. Other one is dy by dx equal to b minus square root of b square minus 4, here it is 0, that is why you get the same ODE. So, you can both the ordinary differential equation becomes 1. So, this becomes simply y by x. So, if you solve this, dy by y equal to dx by x. You solve this, you can get log y minus log x equal to log c1. So, this will become c1 is arbitrary constant. So, you have y by x equal to c1. So, this is your xi variable, xi is y by x. So, what is your eta? You could get only one variable in the parabolic case. So, eta is, you choose eta, okay. I choose eta in such a way that the Jacobian of xi and eta has to be non-zero. How do I choose? I choose a simpler form, that is I simply choose as y, okay. If I choose this as y, what is the Jacobian? Xi x, that is minus y by x square, xi y, that is 1 by x, and eta x 0, eta y is 1. This is your Jacobian, okay. So, this is simply minus y by x square, which is non-zero clearly. Where is it non-zero? If your domain is, strictly speaking, this is non-zero only in the domain when y is not equal to 0. So, except you have to consider the domain minus this x axis. So, you have to consider either upper of plane or lower of plane, in which if you consider this Jacobian is non-zero. So, as we have seen earlier, this is only one dimensional domain. You can consider the equation in this domain and in this domain separately, so that you can get your reduced equation canonical form as in this domain separately and in this domain finally is valid even here by taking continuity of it. So, with this Jacobian is non-zero. So, you have these new variables, xi is this, y by x, eta is y. So, what we need is all xx, uxx and uyy and uxy. So, just do little calculations here. So, you have ux, start with ux, that is u xi into ux. So, ux into xix is y by x square into u xi plus u eta into eta x. Eta x is 0, so that is 0. So, this simply you get this only. Okay. So, what is my y by x? Y by x square equal to, you can write this as y by x, y is y equal to eta. So, you have eta y by x square I have to write in terms of xi and eta. So, y is eta, x square is y square by xi square, y is eta. So, eta square by xi square. So, you simply get xi square by eta. Okay. Xi square by eta is my y by x square. So, into uxi. This is my ux. So, that will give me what is my dou x. Dou x is minus xi square by eta dou xi. So, that we can write now uxx, that will be minus xi square by eta dou xi acting on this ux. Ux is minus xi square by eta u xi. This is a function and this is operator. So, minus minus plus xi square by eta. Now, you differentiate this with respect to this product of functions. Okay. So, this is xi square by eta, u xi is 2 xi by eta into u xi plus xi square by eta u xi xi. So, this will give me, that is it. Okay. So, this is my uxx. Now, you want uy, uxy. So, you calculate your uy, that is uy, if you calculate, what is uy? Uy is u xi into xi y. Xi y is xi y from here, xi y is 1 by x plus u eta into eta y. Eta is y, so it is 1. So, you have 1 by, you need 1 by x. What is 1 by x? 1 by x is xi by eta. Xi by eta is 1 by x. Okay. Xi by eta is 1 by x because xi equal to y by x, y is eta by x. So, 1 by x is xi by eta. So, 1 by x I replaced with xi by eta into u xi plus u eta. So, this is what is my uy. So, now you can calculate uxy, that is dou x acting on uy. Okay. So, dou x we know, that is simply xi square by eta and dou xi is my dou x and uy is this one. This is xi by eta u xi plus u eta. So, you have this is equal to u square by eta, this becomes 1 by eta u xi. Okay. You are simply differentiating this product of functions plus xi by eta u xi xi plus u xi eta, that is my uxy. Of course, you have a minus here, minus for dou x. Dou x is actually minus of that. So, I missed that minus for the dou x. So, you have minus. Okay. So, this is my uxy. So, you also need uyy. Uyy is simply You from this you can get dou dou y. Dou dou y is xi by eta u xi dou dou xi plus dou dou eta. This is my together this is my u y y. You act this on u y. U y is xi by eta u xi plus u eta. So, this is a function and this is operator. So, if you operate this first xi by eta and now you differentiate this this function with respect to xi, you get 1 by eta u xi plus xi by eta u xi xi plus u xi eta. Okay. So, this is what you will get if you operate this onto this function. Now, you operate this onto this function, you get what you will get if you do this minus xi by eta square, because 1 by eta xi by eta derivative with respect to eta is minus xi by eta square into u xi plus xi by eta u xi eta plus u eta eta. That is what is if you operate this onto this one. So, this is my u y y. Okay. So, from this you can see that this if you take this xi by eta inside, this will be xi by eta square, xi square by eta square, xi by eta. Okay. So, what you are left with is, so you can see that this gets cancelled u xi xi. So, finally, what is your u y y is simply xi square by eta square u xi xi plus xi by eta into u xi eta and xi by eta into u xi eta. So, you have 2 times of that, okay, plus u eta eta. That is it, you got everything as what you require. So, u x x. So, now your equation, that is x square u x x plus 2 x y u x y plus y square u y y equal to 0 becomes, what happens? Just calculate. So, you need what is x? X is, what is x? From in terms of new variables xi and eta. So, 1 by x is xi by eta. So, x is eta by xi, x is eta by xi. So, you have x square is eta square by xi square u x x. You replace this with u x x. U x x is xi square by eta. Okay. So, this if you combine this one, if you rewrite 2 xi cube by eta square, 2 xi cube by eta square into u xi plus xi power 4 by eta square u xi xi. That is what is my u x x. So, you can see that xi is 4 by eta square u xi xi. So, that is my this term. Now, plus 2 times what is my x? X is eta by xi, y is eta. So, you have eta square, 2 is this. So, you have 2 eta square by xi is my 2 x y into u x y. So, you have found what is my u x y. U x y is this, that minus comes here and you have a xi square by eta. Okay. And of course, you can write, you can put together. So, you have you can combine, take it inside. So, you have xi square by eta square u xi plus xi cube by eta square u xi xi plus xi square by eta u xi eta. Okay. That is my second term. Now, combine with y square, that is eta square into u y y. U y y is here. So, you have xi square by eta square u xi xi plus 2 xi by eta u xi eta plus u eta eta of this equal to 0, because equal to 0. Okay. We simplify, you can see that this xi square goes, xi goes 2 xi u xi. Here xi square eta square. So again here 2 xi u xi here minus 2 xi u xi. So this gets cancelled. Okay. And what happens to this part, u xi part, xi cube. Okay. So this goes. Okay. So you have eta square goes, xi goes. So you have minus 2 xi square u xi here. Here plus xi square u xi. This also goes. Okay. So here xi square u xi minus 2 xi square u xi. So together is minus xi square u xi, and here plus xi square u xi. So this together will go with this. Okay. So this one, these two combined with this will go. So what you are left with is simply and you have one more term. So this one, this is eta goes, xi goes. So what you are simply having is 2 eta by 2 xi eta. 2 xi eta minus 2 xi eta u xi eta here plus 2 xi eta. So this will go. So finally you ended up both the terms, everything is gone except last term. So you have eta square u eta equal to 0. Since eta cannot be 0, that is how we have chosen. Okay. If you choose eta in such a way that Jacobian is non-zero, if you choose eta is 0, then Jacobian is 0. Okay. So you have chosen eta such a way that is non-zero, so so eta square cannot be 0, that implies u eta equal to 0. So this is your canonical form. Canonical form for the given equation, for the given parabolic PD, linear PD with variable coefficients. Now I can easily combine this. So u eta is a function of some C1 of xi. You differentiate with respect to eta, you get back this. Now you integrate one more time. You have finally u xi eta will be this will be eta C1 of xi plus C2 of xi. Right. Now you differentiate with respect to eta, you get C1 of xi, this will be 0. So you have this. So this is your general solution. In the old variable, this is the general solution of u eta equal to 0. In old variables, this you get u x y, which is equal to, now eta is y into C1 of xi is y by x plus C2 of xi by y by x is the general solution. General solution because C1, C2 are arbitrary functions, is the general solution of given PD. So this is how you can actually solve some of the equations. You can reduce even if it is either hyperbolic, parabolic or elliptic. So we can reduce into canonical form, and fortunately here we can solve the equation. Now we look at the last example, that is the elliptic case. We consider simply you consider reduce this equation uxx plus x square uyy equal to 0. Reduce into canonical form. So here again routinely a is 1, b is 0, c is x square. So you see that b square minus 4ac is b is 0 minus 4x square. This is always negative, okay, for every x positive, x non-zero, for every x non-zero when x is non-zero. So the domain is when x equal to 0 means y axis. So, this you remove, so that means your domain is either this or this one. So, you separate them and you work with this, each of these domains. What you get is your equation in these domains, okay, canonical form in these domains with the same variables. So, that is how you can do. So, what happens, because this is negative, so the equation is elliptic equation. Given equation is elliptic clearly, and then x equal to 0 you need not consider because this is a one dimensional line. This that is x equal to 0, y axis. Okay. So, the ordinary differential equations for the new variables here is dy by dx equal to b 0 plus square root of b square minus 4ac, that will give me I times 2x by 2a, so that is 2. So, you have ix. Other one dx equal to minus square root of b square minus, that is going to be minus ix. So, if you do this, you have y minus ix square by 2 equal to c1, okay, or you just take this 2 there. So, you have 2y minus ix square equal to c1. Similarly, 2y plus ix square equal to c2. This is how you get your so, this is how if you solve this, you get these two general solutions for each of these ODEs. Now, because these are involving this imaginary number I, so we know how to solve we know how to choose this xi and eta. We simply take, these are complex conjugates. If you take this xi as 2y minus ix square, eta is 2y plus ix square. If you do like this with these xi and beta variables, you ended up like hyperbolic case u xi eta equal to plus lower order terms equal to 0, but xi and eta are complex functions of x and y, complex valued functions of x and y. So, this is how you get one canonical form. So, you always choose real valued variables, real variables. So, what we do is alpha as a real part of xi, so that is 2y, okay, and then beta equal to real part of xi, that is imaginary part of xi, okay, or imaginary part of eta, anything you can choose, okay, minus imaginary part of xi you can consider, because I do not want to work with minus. So, you have x square, anything you can choose, does not matter, okay. So, beta is imaginary part of xi, that is minus x square. So, I do not want minus x square. So, you can see minus eta. So, both are, so you can work with any of these things. If these two are linearly independent, whose Jacobian is non-zero, and real part, imaginary part, these alpha plus beta, alpha beta, these are simply sum of these linearly independent functions, xi plus eta and xi minus eta with some constants will give you my alpha beta. So, with these new variables, you need to calculate uxx and uyy. Start with ux, u alpha, alpha x is 0 plus u beta, beta x is 2x. So, you have 2x, x is root beta into u beta, that is my dodo x. So, implies dodo x is 2 root beta into dodo beta. This is how you get the operator. This will give me uxx as 2 root beta dodo beta acting on 2 root beta u beta, that is ux. This will give me, because it is constant, you can take it out, this is 4 root beta. Now, we operate this onto okay. So, I operate this onto this product of these two functions, I will give you 1 by 2 root beta into u beta plus root beta into u beta beta. So, together this becomes uxx equal to 2 goes, you have 2 u beta plus 4 beta into u beta beta. that is my uxx. What is uy? Uy is u alpha into alpha y is 2 plus u beta into beta y is 0, that is 0. Okay. That is simply u beta into beta y is 0. So, you have 2 into alpha u alpha. So, you have uyy is 2 dodo alpha acting on 2 u alpha. This will become 4 times u alpha alpha. Okay. So, if you combine this now once you know these are the only things you know. So, now the given equation, that is uxx plus x square uyy equal to 0 becomes you can see what happens. What is uxx? Uxx is 2 u beta plus 4 beta u beta beta. What is x square? X square is simply beta. So, you have beta into uyy is 4 u alpha alpha equal to 0. So, this is nothing but 4 beta you can divide. So, first 2 cancels. So, you have ended up u alpha alpha plus u beta beta equal to minus u beta divided by 2. So, this is your canonical form. So, this is the required canonical form. This is the required canonical form. So, it looks like Laplace equation, but it involves first order derivatives, that is why we cannot solve. Okay. This you cannot solve. Even if it is first order terms are not involved, still it is not possible, because it is a partial differential equation, you do not know any method how to solve this one. Okay. So, in the elliptic case, if whatever you do, you may reduce finally only Laplace equation, that is u xi xi plus u eta eta equal to 0 or u alpha alpha. So, any new variables xi and eta or alpha beta, you can see that the equation becomes u alpha alpha plus u beta beta plus lower order terms 0. Even if there are no linear lower order terms, you cannot solve this u alpha alpha plus u beta beta equal to 0, because you do not know any method, do not have method to solve it. We will see the methods later on how to solve this Laplace equation. Okay. So, this is how we can reduce second order linear partial differential equation with constant or variable coefficients into canonical forms. Some of them, after reducing into canonical form, can be solved completely to get the general solution. Some are simply in reduced form. Okay. So, those are called canonical forms. This is how you reduce, and we have actually seen when we work with the wave equation, we are going to solve the wave equation. We are going to define the problems for wave equation, and as a wave equation in the full domain, that is T positive, and in the spatial domain x belongs to full real line, one dimensional wave equation. We have already seen the canonical form and got the general solution. Okay. So, that we make use when we work with the wave equation and its solutions. Okay. So, that we will see in the next video. Thank you very much.